Hi everyone, this is Dr. K. Kannan, Associate Professor, Department of EC, R.M.K College of Engineering and Technology. So in this lecture video, I am going to talk about the basics of electrostatic and the boundary condition in electrostatics. So first one, electromagnetism, the basics. So electricity and magnetism are different facts of electromagnetism. So here, a moving electric charge produces a magnetic field. So changing magnetic fields moves electric charges. So these connections are first educated by Faraday and Maxwell. Einstein saw electricity and magnetism as a frame, so dependent sides of unified electromagnetic force. When magnetic fields from electricity, it is a static distribution of charges produces an electric field. So charges in movement, so that it will produce electric current, produce a magnetic field. So electric current is an example of charges in movement, or we can have it is electron. Look at the diagram. So magnetic field rotated, the current is perpendicular to that rotation. And according to this electric current flow in the thumb rule, so that we can have the movement of the charge carrier produce a current, so that the current carrying conductor produce a magnetic field. According to that we can define. Then what are the examples of electromagnetic radiation? It is amplitude modulation radio and frequency modulus radio waves, including television signals and cell phone communication links, microwaves, infrared radiation, light communication, X-ray communication, gamma ray communication, and this from one another. Then I'm going to talk about importantly it is a boundary conditions between uh, two different media or the same media with some different parameters. The first one I'm going to talk about the boundary between dielectric and dielectric. So consider the electric field existing in a region. It consists of two different dielectrics characterized by epsilon 1 and epsilon 2. So we know that epsilon 1 equal to epsilon naught into epsilon r, where epsilon r represents the relative value and epsilon naught is a constant one. So I can write for electric field intensity for the medium 1, E1 is equal to E1t plus E1n, where t represents tangential and n represents the normal. So I'm going to write the electric field equation for the medium 1 with respect to tangential position and normal. Similarly for E2, E2t plus E2n. So if I am going for the representation, I can represent 0 equal to E1t del W minus E1n del H by 2 minus E2n del H by 2 minus E21. This is the equation for the entire range from the rectangular surface what we are going to consider for the boundary. So that that overall tangential Et is equal to the magnitude of Et, and En represents the magnitude of En, and here we are going to consider del H equal to 0 because at the boundary we are going to consider. So it is E1t equal to E2t. Similarly for flux density it is D. So D equal to epsilon into E, that we know all. So that D1t divided by epsilon 1 is equal to E1t. Similarly E2t is equal to D2t divided by epsilon 2. So finally we can rewrite in terms of flux density it is D1t. So T represents tangential by epsilon 1, which is equal to D tangential for the medium 2 divided by epsilon 2. Now this equation gives the diagram. Look at that. These are the two diagrams. So region 1 and region 2. So boundary between two dielectric. Now for the above region 1 consider one dielectric and region 2 consider another dielectric. And in this dielectric look at that the rectangular path, right? Consider the rectangular and one Gaussian surface. So in the region 1 the tangential component is T1, in region 2 the tangential component is T2, so that it is Et1 Et2. So the height of that rectangular surface it is del H and width is del W. So this is for the electric field measurement, and for electric flux density measurement consider a Gaussian surface, it is a del S. So this Gaussian surface del S, the outward from the top one it is a dn1, and for lower one it is a dn2, where del S it is a surface, so that we are going to represent the Gaussian surface. This is a corresponding diagram. Look at that region 1 epsilon 1, region 2 epsilon 2. So that dn1 dn2. Similarly for the representation of the vector. So theta 1 and theta 2. Therefore, so del q equal to del q means q, it is a charge. So del q it is a variable charges, right? So dou by dou t. So that we can rewrite this one in terms of rho s into del s. So rho s it is surface charge density of the Gaussian surface. That should be multiplied by del s. So rho s into del s. So this can be rewritten as d1n del s minus d2n. So 1n represents medium 1, 2 represents medium 2. So therefore rho s is equal to dn1 minus dn2. So finally, if you are going to consider rho is equal to 0, then we can have dn1 equal to dn2. So similarly, we can rewrite this d in terms of, that is electric flux density in terms of electric field intensity, Et1, I mean E1n is equal to, I mean E21, that should be multiplied by the permittivity of the medium epsilon 1 and epsilon 2. So that E1 sin theta 1 equal to E1 t equal to E2 t is equal to E2 sin theta 2. Then we can rewrite this equation and finally you can conclude with tan theta 1 divided by tan theta 2 equal to epsilon r1 by epsilon r2. So epsilon r1 it is a relative permittivity of the medium 1, epsilon r2 it is a relative permittivity of the medium 2. Then second one it is between the dielectric and conductor. So first one between two dielectric, but here the boundary condition between conductor and dielectric. So the upper one we have conductor and the below one it is a the different values, right? So upper one it is a dielectric and below one it is a conductor. Always you know that inside the conductor the electric field intensity equal to 0. And similarly we can have the permittivity of the medium dielectric, it is epsilon is equal to epsilon naught into epsilon r. So according to this we are going for the derivation. Now look at the diagram. So first one dielectric we are going to find out, and the conductor we have to find out for the rectangular component as well as the Gaussian surface. So that we are going to have the same equation where we are going to substitute E equal to 0. That's all. So that what happened finally you are going to get dn is equal to rho s. And finally we can conclude with, so no electric field intensity may exist within a conductor. So E equal to 0, rho v equal to 0 and E equal to 0. And the second one we know that E equal to minus del v. So since E equal to 0 then del v also equal to 0, then there can be no potential difference between any 2 points in the conductor. That is the conductor is an equally potential body. Then the electric field E can be external to the conductor and normal to its surface. That is dt equal to epsilon naught epsilon r into Et equal to 0, and dn is equal to epsilon naught epsilon r en is equal to rho s. Thank you one and all.